Okay, you're given this trigonometric function here. The original post had f of theta, but I'll use f of x in the explanation. To find the intervals of concavity, we need to find the second derivative and apply the test for concavity. So the first derivative is 19 plus, use the power rule, 38 times the sine of x times the derivative of the inside is cosine of x. For f double prime, the derivative of the 19 is 0, and then over here we have to use the product rule. So if we call this the first function, and cosine of x the second function, or we could put the 38 in front and use the product rule there. That's another way to do it. But the derivative of the first is 38 cosine of x times the second, gives us 38 cosine squared of x. And then the first function times the derivative of the second, the derivative of the cosine would be negative sine. So we have 38 sine times negative sine, gives us 38 sine squared. If I do factor out that 38, you might recognize this as a trigonometric identity, double angle formula. It's easier to solve equations when you write it like that. 38 cosine of twice an angle. We want to know when does that equal 0 for our test for concavity. So if we divide both sides by 38, this will happen when cosine of 2x equals 0. So 2x equals angles that have a cosine of 0. And that happens at pi over 2, 3 pi over 2, 5 pi over 2 as we keep going around the unit circle, and this could go on forever. We want to go far enough out to the right so that when we divide by 2, we get all the places where the second derivative equals 0. So if I divide by 2, for each angle over here, I get pi over 4, 3 pi over 4, 5 pi over 4, and 5 pi over 4 is outside the interval from 0 to pi. So there are your hypercritical numbers, or the places where the second derivative is equal to 0. Put those numbers on a number line, restricting from 0 to pi, because that's the given, and pick test numbers in each subinterval. Like, I just like to take the average of these two and say pi over 8. And so if I put pi over 8 into the second derivative, this is twice pi over 8, which is pi over 4. That's in the first quadrant. So this has to be greater than 0, which tells us that the original function is concave upward, positive smiley face. The average of these two endpoints is pi over 2. Plug that into the second derivative. The cosine of pi is negative 1, so less than 0, concave downward. And similarly for this one, we get concave upward. So there's your intervals of concave upward, and there's your interval of concave downward from pi over 4 to 3 pi over 4. And that means that pi over 4, f of pi over 4, and 3 pi over 4, f of 3 pi over 4 are points of inflection. Let's just take a look. Here's the graph of f of x. The black graph is the first derivative's graph, and the green graph is the second derivative graph. And if we note that the second derivative is 0 at pi over 4 and 3 pi over 4, that tells us, see how the second derivative is positive to the left of 3 over pi over 4, negative between, and positive to the right. And that tells us that the original function, like we discussed, is concave up there, concave down there, and concave up there. And in passing, I'll make note of the fact that the first derivative is always positive, except here at 3 pi over 4. That means that the function is always increasing on that interval, because because the first derivative is basically always positive, except at 3 pi over 4, where it equals 0, there's a horizontal tangent line. And that's what this green dashed line is. Okay, there you go. Hope that helped. If you have any questions, post a comment.